presenting with Noah Greer. Today we're giving a project update on our experimental validation of flow through a TPMS gyroid lattice. The data processing is still in progress, so we'll just walk through where we started, what we've iterated on, and where we are now.
So first, some context. TPMS gyroids combined with metal additive manufacturing have a real potential to outperform traditional heat exchanger architectures like shell and tube or brace plate designs. And they offer a much higher surface area to volume ratio and inherently mix the flow, which is great for heat transfer. Now, the problem is that if you want to simulate one of these, then you need to know what the flow is actually doing inside the lattice. And specifically, you need to know the transitional Reynolds numbers, which is where the flow shifts from laminar through transitional and then into. And this data isn't publicly available in experimentally validated form for gyroid geometries. And that's the gap that we're trying to fill. Experimental validation gives us more confidence that we are simulating the geometry correctly and gives us a real benchmark to compare against.
So our approach is a classic dye injection flow visualization. So we built a clear water tunnel with a damping tank to reduce the pump pulsation, a circulation pump, and a test section in the middle that holds an SLA printed translucent gyroid specimen. We inject rhodamine B dye upstream of the specimen and film it with the camera as it moves through the channels. By varying the flow rate, we vary the Reynolds number, and we can watch the transition from smooth streamlines to eddy formation to fully chaotic mixing.
Now, a quick note on how we're actually getting the Reynolds number. And for our case, it's based on flow rate and hydraulic diameter of the gyroid channels. And for gyroids, this hydraulic diameter comes from the wetted volume and the wetted surface area of the shape. And one thing worth pointing out is that the reservoir is elevated and the test chamber sits at a local minima in the loop. And this creates a water lock, and combined with the damping tanks on either side of the pump gives us a steady flow through the test section.
Quick note on tools before we get into design iterations. We generated the lattice using TPMS Gen. It's an open source generator from GitHub. And for 3D modeling, we use Siemens NX, and we printed the fixtures and the initial pieces with a bamboo X1 carbon. So all the FDM pieces are printed from that. And the resin prints are from an Elegoo Saturn IV Ultra using Soraya Tech Craft Ultra Clear. And then the dye we used was rhodamine B, which is a good contrast against water.
Now, our initial concept was to create a 2x2x2 unit cell monolithic gyroid and print a flow chamber that interfaced with it. We included an injection point on the inlet and outlet that doubled as pressure taps to measure pressure drop across the geometry. Now, while this worked for pressure testing, it was not feasible for optical experiments. The viewport was far too small to see anything meaningful, and we wanted to see effects further along the path than just 2 unit cells.
Since the first gyroid was bonded to the flow chamber, we printed another version with changes that we thought would perform a little better. So the geometry grew from a 2x2x2 to a 2x2x4 unit cell, meaning it just doubles in length, and that allows for fluid effects to be seen further in the flow path. We were still disappointed with the optical clarity and of the resin print, so we began exploring ideas on how to process the internal geometries and what kind of methods would be best to make the part more transparent. We tried 3 methods in succession: wet sanding up to 3000 grit, polishing with a polishing compound, and clear coat spray painting it.
And from this iteration, we realized that in order to achieve the best optical clarity, we'd need access to the internal surfaces of the geometry to apply a layer of clear coat. The geometry changes would need to include changing the unit cell size from 20 millimeters to 40 millimeters and splitting the geometry up into 1x4 unit cells and removing the printed in place wall.
So this is the concept that came out of that. Instead of printing the gyroid as one solid piece, we split it up into 4 separate prints that came together to form the full geometry. We replaced the outer printed walls with corner supports, which exposes every internal surface before assembly, giving us line of sight access for painting. The 4 pieces then get assembled outside and then placed inside the flow chamber.
And before committing to the full build, we wanted to validate the quadrant concept. We scaled up to 80 by 80 by 160 millimeters, and it's the same 2 by 2 by 4 cell count, but the cells are now twice the size. And that dropped our required flow rates, which makes the experiment easier to run, and it also makes it easier to see inside the gyroid. And we printed test pieces and painted them black to visualize the surfaces and confirm that we had clear access to everything. We also realized that since the quadrants are symmetric, a half geometry would perform the same way and be easier to print. And that's what we carried into the next iteration.
This is the current configuration. With this iteration, the flow chamber walls are now a single pane acrylic, which gives us much better optical clarity with less post-processing time. All internal gyroid surfaces are clear-coated before assembly, and the whole thing is bonded together using UV Cure clear resin as the adhesive to glue the gyroid in place and the walls together.
To make sure that we were capturing behavior of the gyroid and not capturing behavior of the pipe diffuser or of the chamber walls, we built a 2-stage conditioner at the inlet. First was a baffled section that breaks up the incoming jet and forces the flow to distribute across the full cross-section of the pipe. And following that is a section of drinking straws that act as a flow straightener.
For testing, we ran 9 cases spanning the expected flow regimes, Reynolds numbers from 38 up to 460. Based on published computational studies, case 1 and case 2 should be laminar, case 3 through 5 should be transitional, and 6 through 9 should be fully turbulent.
And here are 2 examples from a phone camera. On the left is an example that has a Reynolds number of 103 and is expected to be laminar. And on the right is an example that has a Reynolds number of 357, which should be into the expected turbulent regime. Now, there's a large difference between the 2, where the die breaks up almost as soon as it enters the lattice of the turbulent Reynolds number example, where you get the visible eddies and the cross-channel mixing, and the stream loses its coherence very quickly.
So where we are now, the footage from all 9 cases have been captured and are being post-processed. We're tabulating the results along with observational notes for each Reynolds number, so we can identify experimental transition points for comparison to what's been published in computational studies. From there, the output of this work can feed directly into CFD setup. If transition happens where we expect, we can stay with steady RANs for low Reynolds cases, and if we see unsteady behavior earlier than expected, we know that we need to change our approach to capture this unsteadiness.